Let's look at the THC molecule. Again, this is the line structure, but we can pick out a few patterns here. We have a few different types of bonds. We have an oxygen and carbon bonds right here. Let's do that. We have an oxygen hydrogen bond right here. That's it. And then the rest of the molecule looks like all carbon-carbon bonds or carbon-hydrogen bonds. So let's look at each of those separately. So we're going to need to know the electronegativity difference between carbon and oxygen. We're going to need to know it between oxygen and hydrogen, and between carbon and hydrogen, and between carbon and carbon. So I'm looking at the 4 different types of element combinations that we have in the molecule. So let's go through these. And some of these are familiar. We've done them already. So between carbon and oxygen, so carbon is 2.5, oxygen is 3.5, hydrogen is 2.1 for our electronegativity values. So carbon and oxygen, I expect to be polar from our previous examples. So we have an electronegativity value of 3.5 for oxygen minus our 2.5 for carbon. That will give us a difference of 1.0, which is going to be polar. Cool. For oxygen and hydrogen, we have our 3.5 for our oxygen minus 2.1 for our hydrogen. That gives us a value of 1.4. That's also polar. Carbon and hydrogen, we have a 2.5 for our carbon minus our 2.1 for hydrogen. That gives us a value of 0.4. That's nonpolar because it's less than 0.5. Now, carbon and carbon, we still check this. So carbon is 2.5. And the other carbon is also 2.5. So that's an electronegativity difference of 0. So that's clearly nonpolar. All right. So the only polar bonds I have in this molecule then are going to be here at the oxygen-carbon bonds and the oxygen-hydrogen bonds. So this will be a partially negative oxygen and a partially positive carbon bonded to it. I could also do my little dipole arrows here. And then same here, I've got this partially positive carbon, a partially negative oxygen. And then the oxygen-hydrogen bond, which is abbreviated here, that hydrogen is partially positive, and there's a little dipole arrow there. So it looks like I kind of have a region of this molecule that's kind of polar here and polar there. So I have these 2 small regions of polarity. And then I have a lot of nonpolar regions. And so we would say this is polar, except the molecule is so big, we have to ask, well, can just a small dipole moment in a large molecule really make the whole molecule react in a way that's polar? And we're going to find that we have these small polar regions that it actually is going to react more like a nonpolar molecule. And so that's kind of we can create some boundaries for that when we look at our solubility later. So here I would say polarity is very small.